So one additional skill that you need to have when working with redox reactions is being able to balance redox reactions. Now, we're going to just do the very basic, and what happens in redox reactions that you don't see in other reactions is not only do you have to balance atoms, but you also have to balance electrons. And so when you're writing the half reaction, electrons are going to be placed on the reactant side if you're dealing with a reduction reaction, because in reduction, remember, you gain electrons. And so if an atom is oxidized, then you're going to put the electrons on the product side. So let's look at an example really quickly. So, all right, this tells me to put the correct number of electrons in the correct place. Well, iron has a +3 charge when it's a reactant and then a +2 charge when it's a product, which tells me that this is being reduced because it is gaining 1 electron. So I'm going to put the electron on the reactant side, and it's just 1 electron.
Let's look at another example. I've got chromium 2+ producing chromium 4+. So I've got a 2+ charge on my reactant side, a 4+ charge on my product side. So in order to get an overall 2+ charge so that these can be equal, I need to add electrons to my product side, and I need to add 2 electrons to my product side, because then 4+ and 2- would give you 2+.
If you look at this redox reaction right here, zinc reacts with copper 1 ion to produce zinc ion and copper. So what is being reduced? Well, remember, reduction is gain. So which one is gaining electrons, meaning its charge is becoming more negative? Well, copper, because copper goes from a +1 to 0 charge. So copper is being reduced. Well, if it's being reduced, that means it's gaining electrons. And how many electrons is it gaining? Well, only 1 electron, because it goes from a +1 charge to no charge. Zinc is being oxidized, and which means that it is losing 2 electrons because it's going from no charge to a +2 charge. So I'm going to put 2 electrons on the product side. Here's your issue. I need to make sure that the number of electrons I gain equals the number of electrons I lose. So what I'm going to have to do is I'm going to have to take my reduction half reaction, and I'm going to have to multiply that entire thing by 2 in order to make sure that I'm gaining 2 electrons, because I'm going to be losing 2 electrons. So this would become 2 copper ions plus 2 electrons produces 2 copper atoms. And now and only now can I add these reactions together. Notice my electrons cancel out, and what I'm left with is 2 copper ions plus zinc, which produces your zinc ions and 2 copper. So there is a balanced redox reaction, making sure that your electrons are balanced. However many you gain equals however many you lose. So now that you know that there are half reactions, so you've got a reduction reaction and an oxidation reaction, we are now going to put numbers to that. And the term that we use for actually quantifying what's happening in those overall reactions is cell potential. Now, cell potential is how much voltage exists between the 2 half cells. Okay? So we will be able, and I'll explain to you in just 1 second, we'll be able to find the cell potential for a reduction reaction and for an oxidation reaction. And if we actually add those 2 values together, we can find the overall cell potential for the overall reaction that we add together once you have your oxidation and reduction reactions added together. Now, why does that matter? Why do we calculate it? So the cell potential for a redox reaction will let you know whether or not a reaction will occur spontaneously, meaning if you think about, for example, if you think about a waterfall, common sense tells you that water is going to fall from the top and land on the bottom. So when your cell potential is positive, what that means is that overall reaction is going to occur without any outside help. And that means that it is spontaneous. Okay? If, however, your cell potential, which I will show you how to calculate in 1 second, is negative, that is the equivalent of water going from the bottom of a waterfall to the top of a waterfall. And therefore, it's not going to be spontaneous. If water were to do that, there would have to be some sort of outside force pushing the water up, because it doesn't happen naturally. So when we're talking about cell potential for a reduction and an oxidation reaction, when we combine those cell potentials together, that lets us know whether or not a reaction will occur without the need for any help, or if we're going to have to provide some sort of energy, some sort of voltage in order to get that reaction going. And so really quickly as a review, the half cell potential is always going to be listed as the reduction potential.
And if I want to determine the cell potential for an oxidation reaction, you need to take the negative of the reduction potential. And the reason why you need to do that is the oxidation reaction is simply the flipped reaction for the reduction potential, right? Because the electrons for reduction are on the reactant side, the electrons for oxidation are on the product side. So it's simply flipped, which means that the cell potential, you'll simply multiply it by -1 to transform it from a reduction potential to an oxidation potential.
And the last piece of information is
if a reaction is multiplied by a coefficient, we do not multiply the cell potential. So remember when we were calculating our equilibrium constants over the summer and during first year chemistry, we always would raise your equilibrium constant to whatever value you multiplied the entire reaction by, right? So if you multiplied a reaction by 2, you would raise it to the second power. In this case, you do not, if you multiply the reaction by a coefficient, you do not multiply or raise the cell potential to anything, okay? The only thing that you will do to the cell potential is make it negative if you flip the reaction. So to determine the cell potential for a redox reaction, you simply need to add the oxidation cell potential and the reduction cell potential. So let's look at how to calculate each of these with an example. So I'm asking you to find the standard cell potential for this reaction. So fluorine reacting with sodium to produce fluoride ions and sodium ions, okay? So my first task is to figure out what is being oxidized and what is being reduced. So if you look, sodium goes from Na with no charge to Na+, which means it's losing an electron, therefore it is going to be oxidized. Okay? So I've got my 2 sodiums plus my 2 sodium ions. I have to make sure that I'm balancing my electrons, just to be careful. So keep in mind, since I have a no charge on my reactant side and a 2+ charge on my product side, that means I have to have 2 electrons on my product side, so I have overall no charge. All right? Now, my reduction potential for sodium is -2.71 volts. So, based on what we just talked about, the oxidation cell potential would be simply the negative of that since I have flipped the reaction, right? Since this reaction is oxidation, which is the flipped version of the reduction. So instead of -2.71 volts, it's going to be +2.71 volts, all right? The reduction half reaction would be fluorine. Notice that fluorine on the reactant side has no charge, while on the product side it has an overall charge of 2-, 2 -1 charges, which means I need 2 electrons on my reactant side. So notice when I created this reaction and I gave you the full complete reaction above, it was actually already balanced, which we just talked about earlier. Okay? So now when I add those 2 reactions together, I would get that final reaction. Okay? All right, so fluorine's reduction potential is +2.87 volts, and that's what I'm going to use because I am actually using the reduction half reaction for fluorine. Okay, and as noted above, to find the standard cell potential for this entire reaction, all I have to do is add up the cell potential for the oxidation half reaction and the cell potential of the reduction half reaction. So I'm simply going to take +2.71 and add to that +2.87, and I get +5.58. And please be careful and make sure to include your units, which is volts. So let's look at one more example. So for here, I give you the reduction potentials for aluminum and iodine. Okay, so let's figure out what's being oxidized. Well, aluminum goes from a 0 oxidation number to a 3+, which means it is being oxidized. Okay. In order to balance this properly, notice I have no charge on my reactant side for aluminum. I've got 2 3+ charges on my product side, which means I have a total of 6+, which means I need 6 electrons. The reduction cell potential for aluminum is -1.66, which means the oxidation potential is going to be the negative of that, so +1.66 volts. Okay. For reduction, I've got iodine, okay, I2, which has no overall charge, becomes 6I-. So again, I need to make sure that my charges are balanced, which means I need to add 6 electrons to my reactant side. I have the reduction potential for iodine already. It's +0.536, so I'm going to keep it as that. And so to determine the cell potential for this overall reaction, you simply add the cell potential for the oxidation and cell potential for the reduction, and I get +2.196 volts. The question might be, well, why do we care if the cell potential is positive or negative? Okay? If you have a positive cell potential, what that tells you is that the reaction is going to proceed spontaneously. And what that means, spontaneously, means without any sort of outside help, without any input as far as energy is concerned. The other term that we use when we're talking about whether a reaction is spontaneous or not, we say if it is spontaneous, we say it's thermodynamically favorable. Okay? So some examples of spontaneous or thermodynamically favorable reactions that you experience in your everyday life. Iron. Iron rusts, so it reacts with oxygen. That is a spontaneous reaction. You don't have to do anything, it's going to happen. Now, a spontaneous reaction or a thermodynamically favorable reaction does not necessarily happen quickly, as is the example with rust. It happens very slowly. The whole point of spontaneity, though, is that you don't have, no outside input has to be put in order for it to occur. So if your cell potential is positive, then the reaction is spontaneous or thermodynamically favorable, as we like to say. If it is negative, if your cell potential is negative, then it is not thermodynamically favorable. So I just introduced the concept of spontaneity, or that a reaction is thermodynamically favorable. And there's one last concept that I'm going to introduce in this lesson, and that is Gibbs free energy, because the Gibbs free energy is actually a value that we can use to determine if a reaction is spontaneous or not. Okay? So here's the formula for Gibbs free energy. Okay? Your N is your number of moles of electrons. Okay? So it's the number of electrons that are transferred from your reactants to your products. F is Faraday's constant, which will always be given to you. Its value is 96,485 coulombs per mole of electron. And then E is your cell potential, which we just looked at calculating. Okay? Just a quick note about units. You don't have to memorize all of these different units, but what you do need to recognize is that the cell potential, whose units are volts, that's the same thing as saying joules per coulomb. Now, the reason why that's important is you need to recognize the fact that your delta G, your Gibbs free energy, when you calculate it, its units will be in joules. Okay? All right, so what does Gibbs free energy have to do with whether or not a reaction is spontaneous or whether it is thermodynamically favorable, as we say? Well, if your delta G, which is measured in joules, is negative, then the reaction is going to be thermodynamically favorable. Okay? Now, this makes sense based on what I just talked about with cell potential. If your cell potential is positive, Faraday's constant will always be positive, N will always be positive, which means your delta G will be negative. So since we said that when cell potential is positive, your reaction is spontaneous, it makes sense that when your delta G is negative, the reaction is going to be thermodynamically favorable, or it will be spontaneous. If it's positive, if your delta G is positive, then the reaction is not thermodynamically favorable. All right, so let's actually go back to the two example problems we just did in calculating the cell potential and determine the Gibbs free energy. So here's my equation. Okay, for the first example we just did, we calculated the cell potential and we said that it was positive 5.58 volts. If you look back at your half reactions, you'll see that we transferred 2 electrons. So my number of moles of electrons is 2. So I'm going to plug in all of those values into the equation above, and I get a delta G of negative 1,080,000 joules. Now I'm going to convert that into kilojoules just to make it a more reasonable number by simply dividing by 1,000. If I ask for it in kilojoules, please convert, but otherwise you can leave it in joules, that's fine. Okay? My value for delta G is negative, which tells me that this reaction is going to be spontaneous, which is consistent with the cell potential being positive, which also told me that it was going to be spontaneous. All right? So this was the second example that we looked at. Okay? My cell potential that we calculated was positive 2.196, which tells me this is going to be spontaneous, but let's confirm using my delta G, calculating my delta G. If you looked back, we transferred 6 electrons. So now when I plug this into my equation for my Gibbs free energy, I get negative 1,270,000 joules. I'm going to convert that into kilojoules just to keep it nice and small. So my delta G is negative, which tells me that this reaction is spontaneous. Just as a quick reminder, spontaneous simply means that it will occur without any outside input. That does not mean that a reaction will occur quickly. It could be really slow and still spontaneous, and it potentially could require something to get it started, right? Because it could potentially, the reaction itself could potentially have a high activation energy. So if a reaction requires a spark or something like that to get it started, that doesn't mean that the whole reaction is not spontaneous. once a reaction gets started, if it continues without any outside input, then it is spontaneous. So a good example of that would be any sort of combustion reaction. In order for combustion to occur, you need some sort of spark to get it started because it has a pretty high activation energy. But once it gets started, it's spontaneous. So we consider combustion reactions to be spontaneous.